Welcome to Future Forward, your weekly dive into the bleeding edge of technological innovation. This week, we're peering through a kaleidoscope of breakthroughs that are reshaping our understanding of everything from robotics and biology to energy and computation. Imagine a world where robots move with an almost uncanny grace, learning from observation alone. Picture unlocking the very secrets of life itself, revealing how proteins interact in ways previously unimaginable. And consider, just for a moment, the possibility of truly clean, abundant energy powering a sustainable future, all while quantum computers finally begin to shed their fragile skin and step into practical application. These aren't distant fantasies. They are nascent realities being forged right now, powered by advancements that are redefining what's possible. We're exploring how diffusion models are giving robots intuition, how machines are learning through observation, how AlphaFold 3 is rewriting biology, how we can stabilize solar energy, and how quantum computing is inching closer to viability. Join us as we unpack these revolutionary developments and explore the profound implications for tomorrow's world, a world rapidly being built by ingenuity and innovation. This survey paper explores the burgeoning field of using diffusion models, a powerful class of generative AI previously dominant in image generation for robotic manipulation tasks. It details three key contributions. 1. Diffusion models for motion prediction. Diffusion models are being used to predict future robot joint positions and velocities given current states, significantly improving planning accuracy compared to traditional methods, especially in cluttered or dynamic environments. 2. Generative inverse kinematics. Instead of solving inverse kinematics (IK) directly, diffusion models generate optimal IK solutions for complex poses, allowing robots to achieve tasks that are difficult or impossible with standard IK solvers. 3. Symbiotic transfer. Diffusion models demonstrate promise in bridging the gap between simulation and real-world robot learning by generating robust policies less sensitive to discrepancies between simulated and physical environments, a critical challenge in robotics. Imagine robots capable of not just following instructions, but intuitively adapting their movements based on what they imagine will happen. Next, diffusion models are making this a reality. This technology could lead to more adaptable, robust, and user-friendly robotic systems for manufacturing, logistics, healthcare, surgical assistance, and even household tasks. It potentially lowers the barrier to entry for robot deployment in complex environments. Robotics researchers need to deepen their understanding of diffusion model theory. Engineers should focus on developing efficient hardware capable of running these computationally intensive models in real time. Educators must integrate this new paradigm into robotics curricula. From generating images to guiding robotic arms, let's shift our attention to advancements in materials science. This research introduces a novel self-supervised learning approach for kinesthetic imitation teaching robots to mimic human movements without explicit labels. 1. Multiview, contrastive predictive. Coding MVCP. The model learns by predicting future joint angles based on past observations from multiple viewpoints, e.g., camera and force sensors. This forces the robot to build a rich, internal representation of human motion patterns. 2. Self-supervision. By avoiding labeled data, this method allows robots to learn from vast amounts of readily available demonstration videos. 3. Improved generalization. The MVCP approach leads to better generalization across different humans and environments compared to traditional supervised learning methods. Could a robot learn the nuances of human movement simply by watching a new self-supervised method brings us closer to that possibility. This reduces reliance on expensive, time-consuming motion capture data for training robots, accelerating development in areas like assistive robotics and industrial automation. Wider accessibility to robotic skills is likely. Robotics engineers should explore integrating this approach into existing robot learning pipelines. Developers need to build datasets of unlabeled human demonstrations. Researchers must investigate the robustness of MVCP to noisy or incomplete data. From imitating movements, let's move on to understanding how AI is revolutionizing drug discovery. DeepMind's AlphaFold 3 significantly expands the capabilities of its protein structure prediction model. The key advancements are: 1. Beyond protein structure, AlphaFold 3 can now predict interactions between proteins, DNA, RNA, and small molecules critical for understanding biological processes and designing new therapies. 2. Increased accuracy for complexes. It accurately predicts the structures of protein complexes, multiple interacting proteins, which were previously extremely difficult to model. 3. Integration with databases. The predicted structures are being made available through a public database, accelerating research across various fields. What if we could unlock the secrets held within every interaction in our cells? AlphaFold 3 is providing an unprecedented window into biology's intricate dance. This has immense implications for drug discovery, identifying potential targets and designing drugs, understanding disease mechanisms, and developing new biomaterials. It accelerates biological research across numerous disciplines. Biologists need to learn how to interpret and utilize the AlphaFold 3 data. Computational biologists must develop tools to integrate these predictions into existing workflows. Pharmaceutical companies should incorporate this technology into their drug discovery pipelines. From understanding molecular interactions, let's explore a potential revolution in energy storage. This paper details a significant improvement in the stability of perovskite solar cells, a promising alternative to silicon-based panels. The key innovation is 1. Interface engineering. Researchers used self-assembled monolayers, SAMs, ultra-thin organic layers at the interface between the perovskite material and other cell components. 2. Passivation of defects. These SAMs effectively passivate defects in the perovskite layer, preventing degradation caused by moisture and oxygen. 3. Improved longevity. The resulting solar cells demonstrated significantly improved operational stability, retaining over 90% of their initial efficiency after hundreds of hours of continuous operation, a crucial step toward commercial viability. Could inexpensive, efficient solar energy become a reality? A new interface engineering technique is boosting the lifespan of perovskite cells. Widespread adoption of stable and affordable perovskite solar cells could drastically reduce reliance on fossil fuels and accelerate the transition to renewable energy sources. This has implications for global climate change mitigation. Materials scientists should focus on developing even more effective SAMs. Manufacturers need to scale up production processes, incorporating these interface engineering techniques. Governments should incentivize research and development in perovskite solar cell technology. From enhancing solar cells, let's move on to a fascinating development in quantum computing. This paper presents a novel architecture for quantum error correction, QEC, that addresses the crucial challenge of maintaining qubit stability in quantum computers. 1. Scalable surface code implementation. The design uses surface codes, a leading QEC approach, but with an innovative layout enabling easier scaling to larger numbers of qubits. 2. Reduced connectivity requirements. It reduces the required connectivity between qubits, which simplifies hardware fabrication and improves performance. 3. Demonstration of error suppression. Experimental results show significant suppression of errors using this architecture, bringing closer a fault-tolerant quantum computer. Building a truly useful quantum computer requires taming its fragility. A new architecture for error correction is paving the way toward that goal. A scalable and efficient QEC architecture is essential for realizing the full potential of quantum computing, impacting fields like drug discovery, materials science, and cryptography. It unlocks complex calculations previously impossible. Quantum hardware engineers need to focus on building qubits with the required connectivity. Software developers must optimize algorithms for this new architecture. Physicists should continue researching advanced QEC techniques. From correcting errors in quantum systems, we'll now transition to discussing advancements in brain-computer interfaces. I hope these reports are helpful and fulfill your request. Let me know if you'd like any modifications or further explorations. And that's our look at this week's groundbreaking research. It's easy to feel overwhelmed when faced with such rapid technological evolution. We are standing on the precipice of profound change, and there are certainly uncertainties ahead. Ethical considerations around increasingly sophisticated AI, the potential for unforeseen consequences in complex biological modeling, the challenges of scaling up quantum computing beyond the lab. But the overriding theme here is adaptation. The ability to learn, evolve, and embrace these new tools will be paramount for all of us. This isn't about fearing change, it's about shaping it. We encourage you to engage with these ideas. What excites you most about these advances? Where do you see the greatest potential and the biggest risks? Let us know in the comments below. And if you want to stay ahead of the curve, be sure to subscribe to Future Forward wherever you get your podcasts and enable those notifications so you don't miss an episode. The future is being written now, and we're here to help you understand it. Until next time, keep looking forward